Hello everyone, hope you all are doing fine at your places and hope you all are safe. We have discussed a chapter quadratic equations of 10th class and we have just finished the chapter in the previous video. Today let's start with another chapter of 11th class NCERT book. That is a very interesting chapter and most of the students enjoy doing sums of this chapter. This is mathematical induction. So in this video, we will be discussing what is mathematical induction and we will understand the topic with the help of some examples. All right. So firstly, what is mathematical induction? According to book, it's given that there was a principle known as conjecture, and the mathematical induction is a kind of motivation that is taken from that conjecture concept. So like for example, here is a statement that Alex is a man and there is a second statement that is all men are mortal, that they can die, they are not immortal. So the result of these two statements will be Alex is immortal. Clear? These kind of deductions are known as conjecture. But what is a mathematical induction? Now, mathematical induction is a kind of principle which is used to prove most of the theorems which are including natural number n. So there are a number of results that you have studied in your lower classes as well as you are studying in your 11th standard that are involving the natural number n. And we can literally prove these results using the principle of mathematical induction. So how is mathematical induction applied and what is it actually? I'll go with the example that is given in the book only. Suppose there are tiles and these are placed in this position. Now you know that when the first tile will fall, the other tiles will also fall. So mathematical induction states that in order to make sure that all the tiles will fall, we have to make sure that first tile falls and the other tiles, the following tiles must fall as well. Necessarily false. Okay, it means if the first tile is falling, then second must fall. If the second is falling, then third must fall. Only then we will be able to know that all the tiles are falling. And firstly, we have to have a look that if the first tile is able to fall or not. All right, these are some of the concepts, or these are some of the steps you can say which are involved in the principle of mathematical induction. So what you have to do in case you have to apply the principle of mathematical induction, there are three steps involved. If for example there is a formula that is 1 plus 2 plus 3 up to so on, n is equals to n plus 1 upon 2, we have to prove this result. So we will be following two steps. The first step, which forms the basis of mathematical induction, that is this result should be true for n is equals to 1. Firstly, we have to check if this result is true for n is equals to 1. If it's not true for n is equals to 1, means you are not going ahead and this result is false. You can write. And second, if it is true for n is equals to k, where k is any positive integer, it must be true for n is equals to k plus 1. Alright, these are three steps, basically two, but they can be divided into three. Firstly for 1, then for k, then for k plus 1, correct? Now these are the steps that you have to apply in order to prove any formula which is given in the form of this or which is involving n as a natural number, correct? So let's start with some of the examples to make this concept a bit clear. This is very first example of exercise first, that is exercise 4.1, And in this we have to prove that this is equals to this. If we expand this formulation, we should get this. Now we will apply the principle of mathematical induction step by step. All right, there are some of these sentences which are also very mandatory to write in the statement, write in the solution of the sum, but I'm not going to write because it will only waste time. You can see yourself and I'll be speaking those sentences for you. So firstly, you have to consider that the given statement or the given term or the given formulation or the given equation is P of n, that is 1 square plus 2 square plus 3 square up to so on plus n square is equals to n plus 1 2n plus 1 upon 6. You have to let it equal to Pn. Firstly, we will prove the result for n is equals to 1. Okay, now put n is equals to 1. What will you get? P of 1. We have to find P of 1. Now when you will fill n is equals to 1 in the left hand side, what will you get? 1 square plus 2 square plus 3 square up to so on 1 square. Now you can see and simultaneously put 1 here as well. 1 plus 1, 2 multiply 1 plus 1 divided by 6. Now you can see if a series is starting from 1 square and ending at 1 square, it means there is only one term in that series, that is only 1 square. It means 1. So 1 must be equal to 1. Let's see if it is equal to 1 or not. So 2, then 3 upon 6, which is equals to 6 upon 6, which is equals to 1. So you have to write that result is true for n is equals to 1. Correct? Now we have studied previously that if the results is true for n is equals to k, so it's a condition that if result is true for n is equals to k or not. So let's suppose you have to assume that result is true for n is equals to k. So if it is true for n is equals to k, then n is equals to k must be satisfying the given equation. So just substitute 1 square plus 2 square plus 3 square up to so on k square is equals to k plus 1 2k plus 1 upon 6, right? So you have to prove the result for k plus 1. You have proven for k is equals to 1, n is equals to 1, and then we have assumed for n is equals to k, and now you have to prove the result for n is equals to k plus 1. So you have to prove that P of k plus 1 is also true. Now what will you do? You just have to take one term ahead of this term. Now if it's 1, it's 2, it's 3, it means 1 is adding. Now one term after k will be k plus 1. So it's being squared everywhere, so that is why the term will also be squared. So what will you write? K square plus k plus 1 whole square. Correct? And on the right hand side you will also add the same term which you have just added in the first term. That is k plus 1 2k plus 1 upon 6 plus k plus 1 whole square, because of course you will add on the right hand side as well just to maintain the concord of the equation, right? So this is already done. Look at this statement. We want to write k plus 1 at the place of n, and it's already done. So here it should be k plus 1 whole square, and left hand side is already satisfied. Now we have to satisfy the right hand side with k plus 1 as well. So this is a quite a bit easy trick that I'm going to tell you, that firstly put k plus 1 in place of n in your statement, that is k plus 1. Here you will get k plus 1, then k plus 1 plus 1, that is k plus 2, then 2 multiply k plus 1 plus 1, that is 2k plus 2 plus 1, that is 2k plus 3. Your answer must be k plus 1 k plus 2 multiply 2k plus 3. So we have to make these kind of terms from our right hand side. So I am not going to write left hand side because it's already proven. Okay, so we'll solve the right hand side further. What will you get? Firstly take the LCM. You will get k plus 1, then 2k plus 1, then plus of 6k plus 1 square divided by 6, right? Now when you will solve it, you will get k plus 1 as a common factor. Firstly get k plus 1 as a common factor. It's common, right? So here you will get k multiply 2k plus 1 plus 6k plus 6, correct, divided by 6. Now you have to get k plus 1 and you have already gotten k plus 1, right? Over 6 it's already got. Now we want to get k plus 2 and 2k plus 3. So what will we do? It's pretty much clear that inside the bracket it's becoming a quadratic equation. 2k square, that is 2k square, plus k plus 6k, that is plus 7k plus 6, divided by 6. Now it's a quadratic equation. You can solve it very easily. You can watch the video of 10th class quadratic equations chapter, which we have already done, and I will post the link in the description for your ease, so you can watch that video of factorization and you can solve this thing very easily. K plus 1 upon 6 will be here only. The factors will be, we have to find two digits. On multiplying those we should get 12, and on subtracting or adding those we should get 7. So none other than 4 and 3. So what will we get? 2k square plus 4k plus 3k plus 6, correct? Now just factorize it. You will get k plus 1 upon 6 and 2k, then inside it will be k plus 1 plus 3. Take 3 as a common. You will get 2k k plus 2, I'm sorry, and there again k plus 2. So you can take k plus 2 as a common factor, right? So k plus 1 multiply k plus 2, then remaining part is 2k plus 3 and upon 6. So after finding this, you can write that result is true for n is equals to k plus 1. It means result is true for all natural numbers n, because when we have substituted k plus 1 in place of n in the statement, it was becoming this, and we have modified our statement, the right hand side as well as the left hand side, in the same way that we wanted. Okay, so it means the result is true for n is equals to k plus 1 as well. So this is where the sum ends, and the trick or the complication in this sum is only here when you have to add a certain term on the both sides. But it's very easy. You just have to fetch the next term, the following term from this term, and then you can add the same term on the both hand side. Then you just have to solve and simplify it as much as you can to get the desired answer. All right, but it's not every time that you have to add something. Sometimes you can you have to multiply as well, because it totally depends on the nature of the equation which you are getting as a sum. Okay, so let's move to the next example. This is our second example. We have to prove that 2 raised to power n greater than n for all positive integers n. So firstly, we'll follow the same steps that we have just followed in our first example. Firstly, let it be p of n, that is 2 raised to power n greater than n. Now it's a statement which is involving an inequality, not equality. Okay, so that is why we'll solve it that way. Now firstly, we have to find that if it is true for n is equals to 1. So substitute n is equals to 1. What will you get? 2 raised to power 1 greater than 1. This implies 2 greater than 1, which is true, because 2 is greater than 1. So that means the result is true for n is equals to 1. Now what's the next step? Assume that it is true for n is equals to k as well. So put n is equals to k. You will get 2 raised to power k greater than k. Now this is the equation that you have got, right? Now we have to see that can we prove it for n is equals to k plus 1 or not. So firstly, before proceeding, every time just substitute n as k plus 1 in the statement in your rough work. 2 raised to power k plus 1 greater than k plus 1, right? So this is the answer that we have to fetch, that we have to get. Okay, so this is the answer that we have to get. Now here it is no series. In the first example, we added the same term on both hand sides because there was a series going on, and it was pretty much easier for us to fetch the term that was following the last term, right? But here there is no series, so we'll just look at our answer and what we have to get. So now we will prove the same result for n is equals to k plus 1, right? On the left hand side it's 2 raised to power k plus 1, but here we have only 2 raised to power k. It means 2 raised to power k needs to be multiplied with 2 raised to power 1 to get the power of k plus 1. So if we have multiplied anything on the left hand side, the same thing will be multiplied on the right hand side of the first equation. So k multiplied by 2. What will you get? This implies 2 raised to power k plus 1 greater than 2k. Correct? Now we have got our left hand side, that is 2 raised to power k plus 1, but here it should be k plus 1, not 2k. Now we will just decipher this thing a bit. What will you get? 2 raised to power k plus 1 greater than k plus k. Can you write 2k as k plus k, right? Now you can see that k plus k is always greater than k plus 1. Correct? Because it's k plus k and it's k plus 1. So 2k plus 1 is indirectly or directly less or more greater than k plus 1. This is what we were desiring of. Correct? 2k plus 1 is greater than k plus 1. Now you can write the result is true for n is equals to k plus 1 as well. It means the result is true for all natural numbers n, okay, or every positive integer n. Correct? So this is how to do these kind of sums. Just substitute n is equals to k plus 1 in this statement and just look at the statement that what kind of answer you have to get, you have to fetch. Only then you will be able to make the desirable answer. Otherwise it's not easy to simplify after first equation. Okay, so just keep this thing in mind. This is our next example, third. In this, a series is given that 1 upon 1 multiply 2, 2 multiply 3, 3 multiply 4, n plus 1 must be equal to n upon n plus 1. So what will we do? Let's go step by step. Firstly, for n is equals to 1. Now again we have to assume it as p of n, right? I am not repeating the steps because I hope so that you must have understood it till now. For n is equals to 1. If you will put n is equals to 1, on the left hand side you will only get 1 upon 1 plus 1 is equals to 1 upon 1 plus 1. It means 1 upon 2 is equals to 1 upon 2. This implies 1 upon 2 is equals to 1 upon 2. It means it's true for n is equals to 1. Now what will we do? Assume that it's true for n is equals to k. So the series that you will get 1 upon 1 multiply 2, 1 upon 2 multiply 3 up to so on 1 upon k, k plus 1, and on the right hand side k upon k plus 1. This is the equation that you have got. Now we have to prove it for n is equals to k plus 1. So we will take the same equation, equation 1, but we have to write something, a certain factor to left hand side as well as to right hand side. And what was that factor? As I have told you in the example first, that look at the pattern in which the series is going on. It's 1 and it's 2, it's 2, it's 3. It means 1 is increasing. These terms are increasing by 1. And if it's k, then the next term will be k plus 1, and here it will be k plus 2. So what we will add on both sides? The following term, that is 1 upon k multiply k plus 1 plus 1 upon k plus 1 k plus 2, and on the right hand side as well we will add the same term, k upon k plus 1, then plus 1 upon k plus 1 and k plus 2. Correct? This is what we have got. Now left hand side equation is true because in the place of n we wanted to have k plus 1 and k plus 1 plus 1, that is k plus 2. So left hand equation is already done. We have to only solve right hand equation, and what we have to get? We have to get k plus 1 upon k plus 2, because k plus 1 plus 1, that is k plus 2. So we have to get k plus 1 upon k plus 2. So let's simplify the right hand side. Firstly take the LCM, the very first step, that will be k plus 1 and k plus 2 only. You will get k multiply k plus 2 plus of 1 only. Now just solve it a bit. K square plus 2k plus 1 upon k plus 1 and k plus 2. Now you have to make factors again of the quadratic equations. Factorization is very important concept in order to solve the sums of mathematical induction successfully. So by multiplying two digits you have to get 1, and by adding or subtracting them you have to get 2. So it's quite clear that k plus k will be the splitting factors of middle term, and k plus 1 and k plus 2. So k can be taken out as a common factor from first two terms. K plus 1 can be taken out as a common factor from the last two terms, and you will get k plus 1, k plus 2 in the denominator. Now you can take k plus 1 again as a common factor. What will you get? K plus 1 multiply k plus 1, the remaining factor, upon k plus 1 multiply k plus 2. So what will you get? You can cancel the same factors, k plus 1, k plus 1. You will get k plus 1 upon k plus 2. Or you can write k plus 1 upon k plus 1 plus 1. This is the desired result, right? We have to fetch k plus 1 upon k plus 1 plus 1, and we have got the same thing, k plus 1 upon k plus 1 plus 1. Now you can write the result is true for n is equals to k plus 1. That is why the result is true for all positive integers n. This is how you have to proceed with the sums of mathematical induction. Now we are done with the today's video, as these examples are sufficient for you to start your exercise and to try some of the sums. Alright, if you find problem in any of this step, in any example or any sum, don't hesitate in writing me personally on my Instagram account. The link will be given in the description for you guys. You can also use the comment section, and before leaving, don't forget to press the subscribe button so that I can serve you with these kind of videos on a regular basis. All right, it was nice meeting you, and thanks for watching guys. Keep practicing and happy practicing.